Hey everybody, we're back for our second lesson on limits involving trig functions. They're totally different from the other limits we've been studying. And in our last lesson, we proved by example these 4 rules that I want you to memorize. Okay, so this should look familiar. Today, we're actually going to do some examples. So let's take a look at example 1. It says the limit as x approaches 0 of the sine of 3x divided by x. Okay, this is looking strikingly familiar to rule number 3. Take a look at rule number 3 from our last lesson. Rule number 3 says, let me get a different color here, the limit as x approaches 0 of the sine of ax divided by bx is just simply a over b. So a over b. So if you look at this problem right here, you can see that my a is 3 and my b is 1. So the answer to this limit problem is simply 3 over 1, which is 3. Final answer. And I also want to point out, I forgot to do something. We really should, before we start any of these applications here, we really should be plugging 0 in first. So let me actually backtrack here. If I plug 0 in for these x's, I'm going to get the sine of 3 times 0 over 0. And that is equal to the sine of 0 over 0. And I know that the sine of 0 is 0. And the reason I know that, just to remember, is that on the unit circle, at 0 radians, which is here on the right, the coordinates are 1, 0, and I know the sine is the second coordinate. So that's how I know that the sine of 0 is 0. So this results in something undefined. Now, typically, when we were doing our older limits, this is the part where we would, in the recipe, go on and we would factor or multiply by the conjugate. But with this problem, we can't do that. We're not going to factor it. It doesn't factor. We can't multiply by a conjugate because there's no binomial anywhere. And we certainly can't eliminate the complex fraction because there isn't one. So this is a limit involving trig, a little bit different. Had to bring in that third formula here that we proved by example. Okay, let's take a look at example 2. The limit as theta approaches 0 of the sine of 5 theta divided by the sine of 2 theta. Let's start by plugging 0 in for theta, just to make sure that it doesn't come out as a real number. So the sine of 5 times 0 divided by the sine of 2 times 0. And this is really going to be a dead end because this is going to be 0, and from up above we know that the sine of 0 is 0. And here the sine of 0 is 0. So we are undefined. So we're going to have to go on and do something else. Now, this is looking familiar. If I go back to my memorization that I asked you to do, take a look at number 4. Number 4 says the limit as x approaches 0 of the sine of ax divided by the sine of bx is just a over b. So that's the form I have. So if I just take that and apply it here, here's my a and here's my b. So the answer to this limit is simply 5 over 2, or if you want to write it as a decimal, 2.5. And you can totally check these on your TI-84 table. You can make a table, solve the limit numerically, and check that 3 and 2.5 are correct. Okay, let's move on to example 3. Example 3, limit as x approaches 0 of x plus sine x all over x. Okay, we start by plugging it in. That's going to be 0 plus the sine of 0 over 0, which again is going to result in something undefined. All right, now this one's kind of interesting. This gets a little fun because if you look at this format, I am not seeing this exact format as one of the formulas I memorized. But you see number 1, see sine x over x? I do see that within the problem right here. So if I can find a way to isolate sine x over x, I can at least use formula number 1 in some way. So here's what I'm going to do. I'm going to recopy my limit. And using algebra and fractions, I am going to split this up. I'm going to write this as x over x plus sine x over x. Okay, now why can I do that? Well, I have a monomial denominator, and when you have a monomial denominator, you may split each part of the numerator over top. Here's the thing, if that doesn't make sense, think of it backwards. If you were adding two fractions with a common denominator, wouldn't we add the numerators and put it over the common denominator? So instead of adding these fractions to get here, I'm breaking this apart to get here. Okay, now what's cool about this is you can see the sine x over x right here. So let's go a step further. Let's write this as the limit as x approaches 0. X divided by x, I can call that 1 plus sine x over x. Now, we're going to talk properties of limits for a second. Yesterday, I gave you a pink sheet, or if you didn't get a pink sheet, you can just look at mine. On this pink sheet, properties of limits, there is a rule. It's rule number 1. It's called the sum rule, okay? And the sum rule says that the limit of a sum is equal to the sum of the limits. The limit of a sum is equal to the sum of the limits. And there's notation here that you can read to go along with that. But basically, there is a limit rule that says that if you have a limit of a sum, you may break that apart and write it as the sum of two limits. So I can do the limit as x approaches 0 of 1 plus the limit as x approaches 0 of the sine of x over x. And now what's great about this is right here, you can see property number 1 right here. The limit as x approaches 0 of sine x over x is 1. We've memorized that. So now we've got this guy right here. The limit as x approaches 0 of a constant, 1, is just that constant, 1. Because the y value on a horizontal line, if I graph y equals 1, the y value is always 1 no matter what x is approaching. So this is going to be 1 plus this is 1. So the final answer to this limit is 2. And we are done. But see how that took some clever manipulation, kind of thinking outside the box. Okay, last example, example 4. Okay, this is the limit as theta approaches 0 of the cosine theta minus 1 all over theta. We'll start like we always do by plugging it in. So putting 0 in for theta, I have the cosine of 0 minus 1 over 0. Now the cosine of 0. The cosine of 0 is the first coordinate on the unit circle at 0. And that's going to be 1. 1 minus 1 is 0 over 0. And so again, undefined. So I'm going to bring this limit down. And we got to start to think about ways we can solve it. Okay. This is really going to take some creativity on our part. Here's the deal. If you look at this as is, my goodness, I don't see anything remotely close on our sheet that I asked you to memorize. In fact, sine, 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 sine. There is absolutely nothing on this sheet to do with a cosine. So I got to figure out how we're going to turn a cosine into a sine. Not so easy. But I'm going to bring something up here on your green sheet. This green sheet has a bunch of trig identities on it. And I want you to look down here on your left side, about halfway down the sheet, right here. There is a identity, a trigonometric identity you learned in pre-calculus that says the sine squared of theta plus the cosine squared of theta is always equal to 1. Now let me show you why. There's a reason. And it's really, really simple. Think about your unit circle, right? Go in that first quadrant of your unit circle. You know that any coordinates on the unit circle are given by the cosine of the angle, say this is theta. We know the x coordinate, right, corresponds to the cosine of the angle. And we know that the y coordinate corresponds to the sine of the angle. And we know that the radius of the unit circle is 1. So by the Pythagorean theorem, we can say that leg squared plus leg squared equals hypotenuse squared. So sine squared theta plus cosine squared theta is equal to 1 squared, which is just 1. So that's where the Pythagorean identity comes from. And you can plug any angle you like in here or any radian measure. And if you take the sine there and square it, add it to the cosine squared, you will always, always, always get 1. Okay, so why am I bringing this up? Well, you see the cosine squared and the 1 has something to do with the sine squared? And I want to involve sine in my problem here. So here's what I'm thinking. I'm going to multiply the top and the bottom of this problem by the conjugate of the numerator. So I'm going to multiply top and bottom by the cosine of theta plus 1. Cosine theta plus 1. Watch what happens. When I do that, I FOIL my numerator. Cosine theta times cosine theta is cosine squared theta. The outside and the inside are going to cancel out, cosine theta and negative cosine theta. And negative 1 times 1, negative 1. And this is all over theta times cosine theta plus 1. Now, you can see the Pythagorean identity coming to life here. So off to the side, I know that sine squared theta plus cosine squared theta equals 1. This is like side work. So if I subtract the 1 to the left side and subtract the sine squared theta to the right side, I'll have this manipulation. I'll have cosine squared theta minus 1 equals negative sine squared theta. So I'm going to replace this with this. And now I've introduced sine into my problem. So coming down, I've got the limit as theta approaches 0 of negative sine squared theta over theta times cosine theta plus 1. Now, I'm looking for sine x over x, sine theta over theta, not sine squared theta. So I'm going to break this down even further like this. I'm going to trade or change this into this. I'm going to write sine theta over theta because that's what I want. Now, all the leftovers can go beside it. So I have a negative sine theta here, and then a cosine theta plus 1 here. I haven't changed anything. I just rewrote it. Look, sine theta times negative sine theta is still negative sine squared theta, and theta times this quantity is still right here. I've just split them apart. Now, appealing to the pink sheet, the properties of limits. There is a property, number 3, called the product rule, which says that the limit of a product is equal to the product of the limits, much like the sum rule. So my next step is going to be breaking this apart. So I'm going to do the limit of sine theta over theta times the limit of the leftovers, negative sine theta over cosine theta plus 1. And now we're almost finished. This one is one we've memorized. This is 1 times. Now I'm going to plug 0 back in and hope to heavens we don't have 0 over 0. So let's replace the thetas with zeros one more time. This would be negative sine of 0 divided by the cosine of 0, not theta, of 0 plus 1. Okay, well, we know the sine of 0 is 0 times a negative 1 is still 0 over the cosine of 0 is 1 plus 1 is 2. Yay, we do not have 0 over 0. We can do this math. 1 times 0 over 2 is 1 times 0. Final answer to this limit problem is 0. But see how we did it completely by hand, using limit properties, using some trig identities, and we manipulated it multiplied by a conjugate to introduce what we needed. This is a little more outside the box, but it works. And that is how you evaluate limits involving trig functions.